So we're talking about the cashier system in our Mensa. And let's say this is the program that's running in the background. So this is the account system. It starts with balance equal to 0. And there are three methods. One is deposit, one is read balance, and one is withdraw. What deposit does is it uses this balance variable. Whatever you deposit to it, it adds it to the balance. Read balance just returns balance, and withdraw deducts that amount from balance and returns it. Suppose I and let's say Professor Carlo go together and use the two counters simultaneously, and let's say both of us buy the wedge option. So you basically have a deposit of 10 happening at the same time. What do you think the answer will be here? You would assume that if you started at 0, it should be 20. But actually, this dot balance equals this dot balance plus x does not happen in one go. What happens is balance is read, and then you do the update, and then it's returned to the variable balance. So let's say both of them do it simultaneously. Both of them read that the balance is 0, and you add 10 to it in your local copy, and then you write 10 first. Let's say Professor Carlo's 10 gets deposited first, and then this dot balance equal to 10 is happening again in my case. So totally the balance will just be 10 instead of 20. So maybe that's why, Uzi is having toilet paper problems. But what actually happened was there was a data race. So when variables are accessed by different threads simultaneously, and at least one of them is the right axis, data race happens. In this case, balance was a shared variable which was updated simultaneously, and this caused a problem. What do we do then? We know we use locks. So let's say we hold the lock on the account object that was created, A1. Now you would assume everything is good because every time I'm trying to update the balance, I'm holding the lock. So when, let's say I want to do the update as well, I cannot do it because the lock is held by the Carlos, update. So it all looks good. But let's say I go to withdraw 10 and there's a deposit of 10 happening instead of both of the deposits. Now what happens is you're reading the value of balance first and copying it in the local value here. And now let's say you started at 0. So the balance it reads as 0, but actually now there is a deposit happening. Let's say it finished. So now actually the balance is 10. But I'm remembering the old value, which is 0. And now when I hold the lock and update, the balance will be 0 minus 10, which is minus 10. Maybe that's another problem that's happening. So just by holding locks, whenever you access a shared variable, the problem is not solved. So what is this kind of a problem? What really happened here? Actually, the programmer intended the withdraw and the deposit operation to happen in one go, atomically. But he never really specified that intention. And he thought that, okay, this can happen atomically, this can happen atomically, so it's okay. But this kind of a problem is sneaky. We might have seen data races before, but atomicity violation is actually, according to a survey, more common than data races. So right now we saw two different kinds of concurrency properties. And how do we verify such properties? How do we detect such properties? And how do we show that a program does not have any such violations? Let's look at first approach, which is dynamic analysis. This is more close to testing. And let's say Shifat buys a veg option, Marco buys pasta, and I know there's a problem with the system. So what I do is I take this box, which is the delivery box. You can take a deposit of pay 10 and take a deposit. And at the same time, when they're doing that, I go and give it back so that I have to do the withdraw operation. So let's see how can the system detect that there is a problem like this? Okay, so what I do is I'm sorry for the handwritten thing. I was not having a lot of time. So there is a node associated with thread 1 where the withdraw is happening. Because I started doing the withdraw here. Okay, and what that translated to was the transaction began. I acquired the lock, and now I copied it to a local variable, and the lock was released. Now, somebody who is running a monitoring system, let's say Professor Carlo was given this job to detect any bugs. So let's say he set up a monitoring algorithm on the side that does it. So what it remembers is right now, until now in thread 1, balance was accessed. So that schedule is a set which remembers what shared variable was accessed until now. Next, let's say in thread 2, okay, Shifat is depositing 10. So there is an acquired, he updates the balance and releases it. Now, what we really want to do is, what its intention is, okay, I need to make a small point. If you have this definition, it's a very vague definition and you cannot really use it to detect any bugs. Really, another constructive way of putting what this definition, like what this really means, is that whenever there is an operation happening that is meant to happen atomically, you would want it to be equivalent to some sequential execution where there was no interleaving. If there was an equivalent execution where there was no, basically this happened sequentially and you got the same output, in no way if this happened sequentially you would have gotten a -10. You would have definitely gotten a 0. So if you can find an equivalent trace where everything happens sequentially, then you would say that this trace, there is no atomicity violation. So we use that logic, and what this edge really represents is the fact that no matter what happens, this person that's updating the balance should always happen. This particular update should happen after my update. Because if I update the balance before this, it would be reading the wrong value. So here I want this to happen after that. And I remember this information in the conflict set. So now this is over. This transaction is over. So I don't want to forget this information that Shifat's should happen after mine. So I remember that information. And after that, let's say Marco deposits this deposits 7.5. I want to keep this information that this particular transaction also should happen after that. And finally, when I go to do the deduction, I find a cycle. What is this cycle really representing? It's saying that this transaction should happen after this, and this transaction should happen before this. There is no sequential execution where this is actually satisfied, right? I'm saying this should also happen before this should happen after that, which means this should interleave this transaction. And that means that there is no sequential way of either executing mine first and theirs later, or theirs first and mine later. So what really happened in this algorithm was, while I was actually executing, while this run was happening throughout on the side, and another application was running. So there was a continuous monitoring that was happening, and I was keeping track of this graph. The beauty of this graph is the nodes only represent the threads. It does not represent the number of transactions. So if I was running this perpetually for forever, let's say in a 24/7 system, I will have to keep, if there were too many transactions, I would have to have too many nodes to represent it. But this one, if you notice, it is only keeping track of number of threads. And even the information that I'm keeping track of is only about the variables, not how many events there are. So this is a really efficient algorithm. And another advantage of dynamic analysis is, and as soon as there's a problem, I got to know it. Right when this happened, I got to know there's a cycle. So it is real in real time. You can detect the behavior as soon as it happens. Another thing is, suppose somewhere in between it was taking a lot of time. Maybe there was a bottleneck, there was some problem. You actually know what the values are and how the update is happening. And there are many things you can know in real time as and when it's happening. So this is this is an advantage. Another disadvantage here is I only know for this execution that everything is okay. I cannot guarantee anything about any other execution. So that's so there are too many executions possible, and you cannot check this way for every execution. Another thing is that you know you usually have to keep remembering what value is. I mean, basically it can be quite resource intensive. This one is pretty good because actually I'm not keeping track of a lot of things, but most of the usually the dynamic algorithms can be quite resource intensive. So static analysis comes from the first disadvantage, that is unsoundness. So if I want to cover every possible scenario, this may not be easy. So just to take a simpler example now, this was actually supposed to be atomic, but we know that, let's say, somewhere in the program in another thread, this access happened. And I wanted to show, so how many executions are possible? This could execute after begin, this could execute after acquired, this could execute between these two. And there are too many cases. As soon as you have two very long traces, two threads running continuously, there are too many combinations that are possible. But instead of keeping track of every order of execution, every interleaving, just these three are enough. What I'm just remembering is these three are just telling that the X is either coming between these two values, or this X update is happening after the Y update, both the Y updates, or it's happening before both the Y updates. Why are these three enough? Because any value of Y, any possible combination of Y and X is captured in all these three runs. So instead of keeping track of every possible, interleaving, just these three are enough. And this is sort of representative also of it executing here, or it executing here, or it executing here. And this one is representative of everything after that. So instead of keeping track of too many, you are actually abstracting and just remembering what is really needed for you to capture that property. But this has its own disadvantages. Actually coming up with these techniques to find out what is really needed, this is generally quite non-trivial, and also it's about the false positives. What I mean is, this program was really simple. What if there was a while loop here? If you had a while loop, you don't know when it terminates. In a static situation, you don't know when it terminates. You don't know if X and Y really point to the same thing. So you don't know whether you will have to keep track of, if there was another variable, you wouldn't, sorry. Yeah, if you had another variable, let's say Z, you wouldn't know actually if it points to the same thing. So should you actually, how many cases should you consider? This will usually not be very clear. So this is the disadvantage of static analysis. So besides that, these techniques are not just giving you a lot of false positives, but also these techniques are still not very efficient. Unlike if you look at dynamic analysis, it was actually running in linear time. It was running parallelly as and when it was happening, right? And sometimes you can also come up with algorithms which are like constant space, like which really don't depend on how many events there are, but only remember what's required for you to detect that violation. But coming up with things which are polytime and which are also automated is usually quite difficult in static analysis. So that's it. This is the thing that I'm really working on, how to make static analysis more efficient. And this is the end of the episode. So if you want to really know how we do it, you have to come to my prospectus next week.